This is a tutorial on the Kerry-Howard correspondence from a programmer's point of view. I will show some code examples in Scala. What is the Kerry-Howard correspondence from the point of view of practice? What problems does it solve? It is a theory that answers two questions from the programmer's point of view. The first question is, can a program compute a value of type X given values of some types A, B, C, and so on? Typically, X, A, B, and C are type parameters or type expressions made up from type parameters. Here's a typical example. Suppose we have a type signature with three type parameters, and the function has three arguments of these types. So the types of the arguments are type expressions made up from type parameters only. That is a very important detail that I will talk about later. But this is an example of a problem that the Kerry-Howard correspondence solves. Can this function compute its value? So we are required to compute a value of type B given these X, Y, and Z. So for example, we could think, if I could somehow compute an either B and C, let's say some other X, somehow, then I could compute a value of type B. I could map with the function Z, and I can do a merge on the either, and I get a value of type B. But can I implement this X here? Well, I should probably rename this X to something else, but anyway, can I implement this function? The Kerry-Howard correspondence gives formal and rigorous mathematical answer to that. And the answer is negative. You cannot implement this function. But is it obvious? It's not necessarily obvious. It is useful for a programmer to understand that, first of all, this question can be answered unambiguously, and second, there is an algorithm for answering it. In other words, tools could, in principle, answer this question. A compiler or a compiler plugin could answer this question for the programmer, or could verify that the programmer is right. The second question that the Kerry-Howard correspondence answers is, can we infer the code from the type? So it's a very specific kind of inference, is code inference. You're given a type signature and you're trying to derive the code of the function directly from the type signature. So here are three examples of type signatures. Again, these are the type signatures of functions with type parameters such that the arguments are entirely types made up of type parameters. So there are no specific types here like integer or string. They're always only type parameters. That's very important. One example is this: from A to either BC, I also have either AC, can I get either BC? Or from A to either BC, I get either of A to B, A to C. Well, these examples may appear to be quite artificial, especially this one. Just some complicated function of high order. But imagine that in your business logic you have something like this, something like this. It can happen. So the theory of Kerry-Howard correspondence gives an algorithm for answering these questions. One usually says that in these cases you can write code guided by the types. So you look at the types, you try to implement this function, and you, guided by the types, you write the code, somehow guessing what to write. The theory tells you there's an algorithm which explains what it means to write code guided by the types. There's no guessing. And this algorithm can be implemented as a library. So here is a link to an open source library that I implemented some time ago that generates Scala code from type signatures. And this code, for example, can be used like this. You write the type signature and you say equals implement. So implement is a macro which we'll examine the type signature on the left-hand side and try to write the code and compile that code of this type signature. Sometimes there is no code that fits the type signature. Sometimes there's more than one implementation. The library tries to be smart about it and find a useful implementation. So these are the problems that the Kerry-Howard correspondence solves. How does it solve that? So let's consider this example. This is a function which cannot be implemented. But how do we know that it cannot be implemented? Maybe we are not clever enough. Maybe there are some tricks. Maybe there are some library calls that we don't know about. No, actually there isn't any way of implementing this. And you can prove this mathematically, which I will not do in this tutorial. If you put this into the Kerry-Howard library, it will tell you that this cannot be implemented. And the algorithm is not easy to follow by hand, but the programmer should have an intuition for this, and that is quite doable. So I will just explain how this theory works, but I will not actually go through the algorithm for this case. So the idea is to build a system of logical derivation rules and axioms that will answer this question. Is this implementable or not? Now, if you look at these two questions, they're really almost the same question. And the first question is, can it be done? And the second is, how can it be done? And it's actually really the same question. If you know how it can be done, then you also will find out whether it can be done. And there's no other way of trying to answer this question. So really, there's only one question: implement the function given its type signature, or find that this is not possible. So in this case, it is not possible. We will find out how to formulate the logical rules that prove rigorously whether this can be computed or not. So in logic, such statements are called propositions. So the propositions that can be proved true or false. Let's denote CH of B. So CH stands for Kerry-Howard, but also you can interpret this as saying code has a value of type B. This proposition means a function can compute a value of type B in its body, or it can return the value of type B. So what we need is to obtain rules for reasoning about these propositions and for proving them true or false. Now, how do we go about that? The only way of writing code for this function is to write expressions, so specifically expressions like this. We are using a Scala function map, but imagine this is written out in terms of some pattern matching, some basic code, which computes a value of type either AB from values of type either AC and the function C to B. So that is what is happening here. Now, each expression of this kind means that you can compute a value of a certain type given values of some other types, which means we have a logical relationship between CH propositions about these types. So CH of this follows from CH of this and CH of that. So that's a logical relationship that says that one thing can be proved if you can prove the other things. So in logic, the proof task of this kind, when X can be proved if A, B, C are true, it's called a sequent. So sequent is a kind of an elementary proof task to prove one thing given some other things. So assuming that we have proofs of these things, we prove this. And the notation with this symbol, which is called the turnstile, is the sequent. So this is the sequent with premises A, B, C and goal X. So we assume that A, B, C are true, and then X will be supposedly proved to be true. So if we prove this sequence, then we know how to do that derivation. Now, clearly, each expression of this kind means that you already have values y and z of certain types, so say of this type and of this type. And then you are, by just writing this expression, you have constructed a value of type either a, b. So this expression itself can be seen as a proof of the sequent that ch of either a, b follows from ch of either a, c and ch of c to b. And so this is the way that we will logically prove such things. So every expression that we can write gives us a certain logical relationship, which is expressed as a certain sequent in logic. And once we write down all those possible derivation rules, we will achieve what is called a logic, or a system of axioms and derivation rules that allows you to prove things. So sequences that are true without proof are called axioms, and sequences that are true given some other sequence are called derivation rules. So in order to determine all these axioms and derivation rules, basically we need to know all possible code snippets, because as we know, the only way for us to establish these logical relationships is to write some code. So we need to find out what kind of code snippets we can write. And once we establish all those code snippets, we will be able to establish all the derivation rules. Now, it's very important that we now restrict the possible code that we can write. If we do not restrict it, we won't be able to write down all possible code snippets. The Greyhour correspondence requires us to restrict the code in a very specific way, which I call fully parametric. So fully parametric code means that you are not allowed to use any specific values or specific types like integer and string. You're only allowed to use type parameters and values built up from other values of given types. But you're not allowed to put the number 5 into your code, for example. Or you're not allowed to check if some type is integer or not, for example. That is not allowed. This is a very strong restriction. It is actually stronger than the restriction to purely functional code. Purely functional code would allow you to use specific types, like integer, or to check that a type parameter is integer or not. For integer, you do one thing. For non-integer, you do some other thing. Purely functional code is not the same as fully parametric. So it's actually a stronger restriction that we need. And purely functional code is already a pretty strong restriction, because you're not allowing all kinds of external function calls, side effects, and so on. But actually for Greyhour correspondence, you need a stronger restriction. But you get a lot out of that. So what are the possible code snippets that are fully parametric? Well, obviously, you need to give some value of type, say, A, and then once you have that value in your function as a parameter, you can use that. So for example, you can write code like this: val y equals x. So that is kind of a trivial piece of code, but you're allowed to do it. So you can use existing value of type A. You can use it any number of times. You can have a tuple type, which you can create using two values of types A and B. You get the value of type pair AB, and you can use that tuple type to extract values from it, like this, for example. Function type. You can create a function which requires you to write code like this. And here you have some expression that uses the value x, or it may use the value x. And you can use the function, you can apply a function to an argument. Then you have disjunctive types, which are, for example, either A, B. It's a disjunction of different possibilities. You can create a value of this type in two different ways, as a left or as a right. And you can use it by writing a match expression, which will see if it's left or right, and then you can do different things, computing a result of some different type C. Finally, you have a unit type, which you can create. You can always create it. There's nothing you can do with it, but you can create it. So as we have just seen, sequence correspond to code fragments that have specified types and use values of specified types. So for example, this sequence, it corresponds to an expression that uses some previously defined values, say x and y, of types x and y, and itself this expression has type z. So if you're able to write code for this expression, then you have proved this sequence. It's important to notice that sequence only describe the types of expressions and of the different parts of the expressions. They do not actually describe code directly. So you could, in principle, have different code with the same type in some way, in some cases, and that's not described by the sequence. The sequence will be proved if you have some code of that type. Sequence does not describe how many different inequivalent implementations you can have. So because the sequence describe only types, it's easier to reason about them than to reason about code itself. And you get a little less out of it. You only get one implementation, or at least the information that you have an implementation, if you prove the sequence. But the proof itself is, as we saw, some code snippets. So you could try to find different code snippets for the same sequence. So let's see what sequence we have. So each code snippet that is allowed here, and these are all, there are no other code snippets you're allowed to write. What is missing here? For example, recursion is missing. You cannot use recursion with Greyhour correspondence. It will not give you good results if you try to incorporate recursion. Let's write each of these sequences as some notation with this turnstile. So when we say use an existing value, then we had a previous value of type A, and we get a new value of type A. So that means if we have a value of type A, we can have a value of type A. Well, it's kind of a trivial statement, but nevertheless, we need to write it down as one of the derivation rules. So this is an axiom, actually. This sequence is true by itself. It doesn't need other sequence for it to be true. And the proof of this sequence is this code snippet, this one. To create a tuple, we need values of type A, a value of type B. So we need these two as premises, and then we get ch of the tuple. And to use a tuple, we need a tuple. So we write the ch of a tuple2 of AB. I'm using the Scala syntax here for clarity. So ch of tuple2 here is a premise, and then we can get a value of type A. So that we write as a sequence, that the premise is ch of tuple2 of AB, and the goal is ch of A. So similarly with B. And the proof of these two sequences is this kind of code, this _1, _2. Since we are allowed to write that, then we have proven these two sequences. To create a function, we get a function a to b that does not use necessarily any other data, but what we need is an expression here. This expression must be something of type b that may use x of type a. So that is itself a sequence which is this. This expression of type B can be written given a value of type A. So if we're given this sequent, then we can prove this sequent. So this is a derivation rule. A sequent can be proved if some other sequent is given and is proved. To use a function, we just have the premises that we have a function of type A to B, a value of type A, and the goal is that we have a value of type B. And the proof of this sequent is simply this code. To create a disjunctive value, we have two possibilities, and so there are two different sequences. And to use a disjunctive value, we have this match expression, which is this sequent. If you're and the code of this code is the proof of this sequent. If you have a function a to c, because this is actually a function a to c, because this is really just syntax in Scala for putting a function from a of type A to something of type C into the match expression. So this is just exactly the same as if we have x of type either a, b, and two functions of type a to c and of type b to c. So that's what is written as this sequent. Finally, the unit value can be created from no initial data. So then we have empty set as premises, and we can have a value of type unit. So these are all the possible sequence, derivation rules, and axioms that we're allowed to use in the reasoning. Here's a table that summarizes the correspondence between the types and the propositions. These are the different types that we have in Scala. And these are the corresponding propositions. So in logic, propositions are combined using operations and, or, implies. And we can see easily that the correspondence between the tuple type and the operation and or conjunction in logic is that you can have a value of the tuple type only if you have a value of type A and you have a value of type B. You can have a value of the either type if you have a value of type A or if you have a value of type B. So this is an or operation or disjunction. And that's why I call these types disjunctive types also. The function type, you can have a value of this type if given a value of type A, you could have a value of type B. You would always compute that, but only if you're given a value of type A. So having a value of type A implies that you have a value of type B. That's a logical implication operation. The unit type is always computable. So you can always have a value of this type. So that's the same as a logical constant true that sometimes is denoted like this. And the nothing type in Scala is the type that cannot have any values. So in logic, it means it is false that you can have values of this type. It's always false. And so that's the constant false, sometimes denoted like this. It's a top and the bottom symbol. I used a shorter type notation in this tutorial, which I will briefly introduce now. Instead of logical AND, I write this kind of multiplication symbol, the cross product or Cartesian product in mathematics. Instead of disjunction, I write the plus. And instead of implication, I write a simple arrow, not a double arrow, just easier to write when writing by hand. Instead of true, I just write this 1 with double line. Instead of false, I write this 0 with double line. So now we can translate types into logical formulas and back. So here's an example. In Scala, you have this function duplicates its argument. So in the short type notation, its type is written like this. And in logic, its type is translated into the logical formula, which is that for all types A, if you have a value of type A, then you must have a value of type tuple AA, which is equivalent to having a value of type A and having a value of type A. The type of this function bad is written like this. So if we are given value of this type, given value of this type, given value of this type, can we derive a value of this type or compute a value of that type? Now notice here, instead of option of B, I write 1 plus B, because option is a disjunctive type that is equivalent to a disjunction of unit, or 1 in my notation, and a given type parameter. So the question about the implementability of the function bad is the same in logic as the question of provability of this sequent. As we have seen, we have written down all the possible code snippets in fully parametric programs, and so we have found a set of all valid derivations in the logic of the types. And so we can write it a little more concisely if we use the short type notation instead of the full CH notation. And these are all the axioms, and these are all the derivation rules. Now I added 2 more derivation rules. This was the one we had, create function, but I also added 2 more rules. So one rule adds a new unused premise. So this is a D, which is not used. We can already prove this sequence. So G can be, in the program, G can be computed, a value of type G can be computed given values of these types. But we can have one more value of some other type, which we're not using, and that's okay. So we can still compute a value of type G. It's allowed to not use, to ignore some arguments. That's a necessary rule. And also a necessary rule is to be able to reorder the arguments. So if we can compute G using ABC, then we can also compute it using BAC or BCA or some other order. So order of premises does not matter. So this is another necessary rule. And these are all the rules then. So then the question is, what is the set of theorems that can be derived in this logic? So here's an example theorem. For all A and for all B, A to B to A. Now, in logic, we write a sequent. From no premises follows A to B to A. We do not write this for all A for all B. We just keep it in mind that all the type variables here are always universally quantified outside of the expression, outside of the sequent. How do we prove this theorem? Now, this is possible to prove in the following way. We start with this axiom, from A follows A, and then we add an unused premise. So we use this derivation rule that we can use premise. We can write a premise B, which we're not using. So then we get this sequence. Now we write a create function, which gives us this. So we use this B. Now, as a create function, we can prove this given this, but now we have more premises. That's okay. We can always have more premises. And finally, we use another create function rule, where now A is a premise and B to A is the result. Now here, so instead of B, we use B to A, and we get the final sequent, which is this. So now it means that this is the theorem in the logic. In other words, it can be proved proved in the logic. We have derived this sequence from no premises. Let's look at the code snippets that corresponds to each of the steps in the proof. This axiom represents the expression x, which we're just using. Then there must be some unused variable, say y, of type b. The create function rule is this code snippet. So using y of type b, we return x. You see, the snippet corresponds to this sequence. We have a value of type x and a value of type a, which is x, and the value of type b, which is y. And we return a value of type a, which is x. Now x is defined outside of this code because this is a premise in the sequence. It must be defined before. We already assume that it is defined, so that's the premise of the sequence. And then we get this. So this is the result at this step. Given a, which is x, we get a function b to a. So this is the function b to a. And then the second rule is this code snippet. The second create function rule, which is here. It corresponds to this sequence. So from no premises, we have this function. So this function does not assume that anything is defined beforehand. That means we can write this function fully as a complete Scala definition, which is going to be like this. So we see that a theorem in the logic corresponds to a function that we can implement. And this is by construction. We do not have any rules of derivation in this logic that do not correspond to some code snippets. So when we combine the rules of derivation in the logic, we combine the code snippets. And at the end, we will have a full, complete code of the given type. So it means, first of all, any code expression can be translated into a sequence, but also any proof can be translated back into the code. And if you have the code, then you can retrace which rules have been used, and you can find a proof. So we have a one-to-one correspondence between code and proofs, and between expressions and sequence, and between types and propositions. This is the correspondence that is called the Greyhour correspondence. Here are some more examples of propositions that can be implemented. By construction, all of these being implemented means that they are theorems, so they can be proved in the logic, and they can be implemented as code. To express the Greyhour correspondence more concisely, one says types are propositions, programs are proofs, but they're not exactly the same. They correspond to each other. You need to translate types into propositions, and you need to translate programs into proofs. But this is an example of how you can do that. I'll show another example later. Importantly, non-theorems cannot be implemented in code. Non-theorems are statements or propositions in logic that cannot be proved using the derivation rules and axioms. So here's an example. From 1 follows a. So from true follows a value of some unknown type. Well, this cannot be written. This code cannot be written. You cannot create a value of unknown type a from a unit type, given a value of a unit type. That's not enough information. Similarly, here, you're given either of a, b, and you're supposed to produce an a. But you cannot, if this either happens to be a right of b, then you could not make an a out of it, since a and b are arbitrary unknown types, and none of your code snippets provides you any ways. These are all the allowed code snippets. None of them provides you any way of creating a value of unknown type a from a value of another unknown type b. And similarly, all these cannot be implemented. So for example, this one, you're supposed to return an A, and you're given a function from A to B. But the function from A to B cannot give you an A. It consumes a value of type A, but it returns a value of type B. You cannot call this function unless you already have a value of type A. So, and even if you were able to call this function somehow, you would get a B, not an A. So you cannot get an A out of it. Now, what I just said was intuitive consideration. This intuitive explanation why you cannot write code for these type signatures. But actually, you can prove that it is impossible. You just go through all of the possible rules, and you show that none of them apply. None of them can apply to derive the sequent from no premises. Now, this is actually quite difficult to prove that there is no proof. What if somehow very cleverly I introduce some new premises that I'm not using, and so on and so on? It's actually not easy at all to prove that there is no proof. It's also not obvious to find that it can be proved at all. So here's an example. I already showed this very strange thing. It's not obvious how to write code for this, or even whether you can write code for this. But we will see that this can be mitigated in different ways, but basically we need to derive intuition for this, and when intuition doesn't work, we use the tools, say the Greyhour library, which implements the full algorithm. Now, the full algorithm only works for this restricted type of code, which I was showing here, and this is called the Intuitionistic Propositional Logic, or also it's called Constructive Logic. So logic, again, is a set of axioms and derivation rules for some sequence about some propositions like this. So what kind of logic is this? It's called non-classical because it's different from Boolean logic. So if you look at the mathematical literature, a lot of logic books only talk about Boolean logic or many-valued logic, say three-valued logic, fuzzy logic, but those are all classical logics. This logic is constructive, it's different from classical logics in very important ways. For example, disjunction works differently and implication works differently. Here's an example. From A to B plus C, or B or C, follows either A to B or A to C. Now, this is true in classical logic. If you can derive either B or C from A, it means you can either derive B or you can derive C from A. But this is not true in constructive logic because actually you cannot implement a function of this type. The reason is that this function could return different values, B or C, depending on the value of A. And you cannot decide in advance whether you're going to return a B or a C, but you're required to decide in advance. You need to supply one of the parts of this disjunction in advance as a return of this function. Before you're given a value of type A, you're supposed to make this decision, and you can't, because you cannot compute A to B from A to either B, C. What if this returns C for some values of A? And you cannot find out if it returns always B. It's impossible to find that out. There's no way, no code you can write that determines whether this function always returns a left of B. So none of the allowed code snippets here allow you to make that determination. And this is counterintuitive. So this is actually true in the Boolean logic. It will be true in classical logic, and it's not true in the constructive logic. So it's not really intuitive. This so-called intuitionistic logic, it's not really intuitive. You need to develop a new logical intuition if you want to understand what is possible to derive in this logic. Implications works differently. Here's a formula which is true in Boolean logic. It is not true in constructive logic. again, we cannot write code for the function that returns an A given this higher order function. This higher order function could return an A if we gave it an argument of this type, but we cannot make an argument of this type. So we could never call that function. And so we can never get an A. There's insufficient data to constructively find a value of type A. In Boolean logic, you're not required to find a value of type A. You're required to prove that it exists. And you can prove that if it does not exist, there is a contradiction of some sort. But that's not good enough for constructive logic. Conjunction works more or less the same as in Boolean logic. For example, there's this theorem. If from A follows B and C, then from A follows B and from A follows C. So what is really different about this constructive logic is that in Boolean logic, you can compute a truth value of a formula, which is given by truth tables. And once you look at the truth table, you decide easily whether the formula is true or not, if it's a theorem or not. And in Boolean logic, the truth table can contain only values true and false. In many valued logics, it can have more truth values, say 3 or more truth values, true, false, and in something in the middle, or many things in the middle between true and false. But Gödel, the quote Gödel of the Gödel incompleteness theorems, proved back in 1932 that the constructive logic cannot have a truth table with a fixed number of truth values, a number of truth values that's fixed in advance, so that you know in advance how to write a truth table. That is not possible. Instead of trying to write a truth table, you have to follow an algorithm or a decision procedure, which is the same, it's just a different word for algorithm. And this either finds a proof for a given formula or determines that there is no proof. Of course, there may be several inequivalent proofs of a given formula. And as we have seen, each proof can be automatically translated into code. This is so because every step of the proof corresponds to a specific code snippet from which we derived that step, which is a derivation rule of a logic. So we can just combine these code snippets in the way that I indicated in that example. And tracing each step of the proof, finally we get the code. So in Haskell and in Scala now there are tools that follow this algorithm and generate code from type. All these algorithms, all these tools follow the same algorithm called LJT, which is presented in this paper. I'm not going to go through that algorithm, it's pretty involved. I'll just indicate how that works. So actually, getting the algorithm is highly non-trivial. We have all the rules here, the axioms and the rules, but they do not give an algorithm. Actually, they do not give an algorithm. So if we write them in terms of sequence, there are too many axioms and too few rules. It does not allow you to find out which axiom to start with. For example, let's try proving this. We need to prove this given these two premises. Are there any rules that allow us to prove this? Well, there's only one possibility. There are two axioms that allow us to prove A plus B given A. Now, we don't have this here. We have A times B plus C, and we're not given C, and we're not given A times B. So we cannot apply these two axioms. So what can we do? Well, on the surface, we don't know what to start with. None of these rules tell us what we start with. But there is a proof. This can be implemented. So if we some cleverly found sequence of axioms and derivation rules does give you this eventually, but it's not obvious to do that. How to do that? Now, from a programmer's perspective, you can start to think intuitively. Well, I need either this or this. Can I get a C? Maybe I can get a C here, but sometimes this will be a B. But if that's a B, then I should return this with an A that I always have. So a programmer can look at this, and having developed the intuition for the constructive logic, the programmer can write code quite quickly for this kind of thing. But these rules do not give an algorithm. We need a better formulation of the logic. The first formulation of the logic that gave an algorithm was found in 1935 by Gentzen, and it was called LJ. And so that was called a complete and sound calculus. Now this is just the terminology that mathematicians use to show that these rules are exactly equivalent to these. So they give all theorems that can be proved and only the theorems that can be proved. So you do not prove anything that's false or anything that cannot be proved using this. In other words, these rules are equivalent to all these. And the difference is that these rules are almost all derivation rules. So derivation rules are written in this syntax like a fraction, where you have a numerator and a denominator. Axioms are written as a single. Well, that's how I write them. But you can write both of them in terms of numerator and denominator, and axioms will have an empty numerator. Derivation rules have one or more sequents in the numerator. So these are assumed, and then you get this. So this is this notation that mathematicians use. So these rules mean in order to prove various things, we need to prove some other things first. And notice how this set of rules is organized. I have put in blue the different expressions that you can have. These are type expressions, the tuple type, disjunctive type, and function type. Tuple type, disjunctive type, and function type. So if you have a tuple type on the left, you can use this rule. If you have a tuple type on the right, you have this rule, and so on. So for any expression that you have, any sequent, you can always find some rule that applies. Your sequent either has atomic prepositions, or it has some type expressions. If you have a type expression, it's one of these three. There are no other type expressions other than these three. And they must be either on the left or on the right or both. And so these rules apply to any sequent, and they give you an algorithm. So just some details that the symbol gamma I'm using here and here, it means any number of other premises. It could be an empty set of premises or some non-empty set of premises. So these rules, as I just described, they can be used bottom-up to perform a proof search. So you start with a given sequent, you go through all the possible rules, and you always find one that matches. If you don't find a rule that matches, that means you cannot prove the sequent. That's the whole point of having these rules instead of those rules. Those rules are not good. They're good for understanding where this whole thing came from, because each one of them directly corresponds to an elementary code snippet. But these rules are good for algorithm building. So a huge amount of work was required to come up with such rules and to prove rigorously that these rules are correct. So given a sequent, we can always look which rule matches, and then we have one or more further sequence to go through, and so on, and that builds a tree, because each sequent can have one or more other sequence that are necessary to prove it. And so it could branch. So start with this, you have 1, but if you start with this, you have 2. So 2 more proofs need to be made. Each of them is again a tree, and so on. So you have this tree of proof search. Here's an example of a full proof search that is performed using this formalism. We want to prove this formula for all R and Q. This function can be implemented. Now in Scala you can easily write a function with type parameters R and Q and type argument having this type and result having this type. To begin the proof search, we write the first sequence, which is this: no premises and this goal. Now we begin the proof search. So which rule applies? We have at top level, we have implication here. And the implication is on the right. So on the right, there are these. You have an implication on the right. It's this rule, R standing for right implication. So there's a right implication, which says that we now need to prove this sequence, which is in the numerator. Let's call the sequence S1. It's going to be this sequence. Now in this sequence, on the right we have atomic value. On the left we have implication. So obviously we need a rule that has implication on the left, which is this rule. Now we are supposed to prove 2 more sequences. Let's apply that. Instead of A we have this. Instead of B we have this. And so it gives us 2 new sequences, S2 and S3. The sequence S3 is the same as the axiom here. It's called id, or identity. So we have proved this sequence. That's fine. Now it remains to prove this sequence. Now this sequence has, again, implication on the left. Let's call again this rule. And it gives us again 2 more sequences, which we call S4 and S5. S4 is this, and S5 is this. Now we notice an unpleasant thing. S4 is the same as S2. We are in a loop. We keep trying to prove the same sequence. We'll never finish. Let's backtrack. The problem with the loop was that we applied rule left implication to the sequence S2. Let's not apply that rule because it gives us a loop. But what else applies to the sequence S2? S2 is this sequence. It has implication also on the right. Let's try to use the right implication rule for it. That gives us 1 new sequence, which is S6, which is this one. The sequence S6 follows from the id axiom because we can use this. This is an unused premise, and this is the same atomic premise as was here. So we can use this id axiom, and we have proved the sequence S6. We're done. We have proved all necessary sequence. Therefore, this sequence is a theorem in the logic. But how do we find code for this? Well, we will find out a little later how to find code. Let me just indicate how the algorithm LJT improves on what we just saw. The problem in this algorithm is that sometimes it gives you the same sequence again to prove, and you're in a loop. But some other sequences are different. So you're not repeating exactly the entire set of sequences that you need to prove. So you don't really know if you're going in the right direction or not. And that's a problem in the algorithm. The algorithm LJT never generates loops. And the way it does that, it removes this problematic rule, or left implication rule, which gives you a loop. The problem is that this rule repeats this premise. It does not remove the premise. And so you are again tempted to apply the same rule. The algorithm LJT removes that premise. It never repeats premises. The cost is that instead of the left implication rule, you have 4 different left implication rules, and they're more complicated. They're quite a bit more complicated because they look at not just this one premise, but what is A in this premise? Is this atomic? Is this itself a product? Is this itself a disjunction? Or is this itself an implication? And in each case, it does something different. And these different things do not repeat the premises. And so it never generates a loop. And actually, it was proven in this paper that there is an explicit measure of complexity on the sequence. And if you go through the proof tree, this measure decreases strictly. And so this shows that this measure, eventually it goes to 0, and then no more rules apply. And so it's either the tree terminates successfully, having proved all the sequence, or it terminates when no more rules apply, having not proved some sequence, which means that the sequence you were trying to prove is not a theorem, it is false. I'm not trying to prove that this is correct, and this is quite difficult. It took literally 45 years in order to 55 years to prove that this is a better non-looping algorithm. I'm just mentioning the main mathematicians who worked on this during this time, from Gensen to Vorobyov to Hudelmeier and Dykov. These are publications that you can find, but the Dykov paper shows this final algorithm LJT, that is a final kind of improved form of the initial algorithm LJ. The new rules are equivalent to the old rules. And so how do we find code? Well, we need to translate sequence into code snippets. And the code snippets are expressions of type G that use values of types A, B, and C. So this snippet does not define A, B, and C. It uses them, and they should be defined before. So that's the premise. But from a programmer's point of view, it is more convenient to see this as a function from ABC to G. And so then each sequence corresponds to a function, and each rule corresponds to transforming one function into another, or one or more functions. So here's an example. This is the rule L plus. It has 2 premises, which are sequence, and the goal, which is this sequence. And so the proof transformer for this rule takes 2 functions, which are functions of type A to C and B to C, because that is how it is more convenient to write sequence. And then it is this code. So it's the match statement. I'm just writing some kind of code notation to save space, but this is exactly the same as a Scala code. X of type A plus B goes to this match expression with 2 case clauses. And I can also write it as a matrix. That's a matrix notation that I developed for match expressions. But let's just not focus on that. here's another example of a proof transformer. It's another code snippet. So the code snippet is a lot more complicated than the code snippets we started with, these elementary code snippets. It's easy to write the full list of those, but it's not easy to come up with these rules. And for each of these rules, the proof is going to be more complicated. So you need to have a function like this, which transforms these curried functions in one way or another. It's pretty involved. So in order to use the LJT algorithm, you need to verify for each of these rules that you have the code snippet. You need to write down the proof transformer for each rule as a code snippet. And that's not going to be so trivial, but it is not a very difficult task. So what do we do to find code, to infer code from type? Once a proof tree is found, we start from the leaves of the proof and we apply proof transformers. So for each sequent, we have some proof expression, which is a function from premises to goal. And for each derivation rule or axiom, we apply the proof transformer. So let's see what it is for that example of this sequent. This sequent was proved using a sequence of steps. The last one was S6. So we need to go from the end of the proof backwards. The last one was S6, and this was this. To prove it, we used the axiom identity. So the code was just this. So the function ignores its premise. The first premise is ignored, the second one is used. The next step was the rule R implication. The proof transformer for the rule R implication is that function. So now we use T6 as an argument of the proof transformer. So we just substitute into the proof transformer. I did not have it here, but you have to write it down. This is the truth transformer for the right implication. It's a function. So you substitute that into that function. This is the code. The result is a function I call T2. So it's a proof term for the sequent S2, T2. We also needed to prove S3, which is this proof expression. Finally, we use the left implication rule, which is going to be this. Applied to T2 and T3. So if I remind you that the left implication rule has two sequences that it needs to have before it can prove this one. So these two sequences, we have proved them before. These are S3 and S2. So we use T3 and T2 here in this proof. And finally, S0 is found using the proof transformer of right implication, which is this. So finally, we have a function that works. This is actually the full code that already works, but it's inconvenient to have such a long expression with 5 different functions. Let's combine them into one. Just substitute T1, T3, and so on. So T0 is this, and you substitute, and then you simplify this symbolically. You simplify evaluating this function as far as you can. And after this partial evaluation, so you evaluate not everything, because you cannot evaluate this. You don't know what that is. That's going to be your argument. But you can evaluate T6, for example. T6 is just R, so it ignores this thing. So that is simplified. And the final result is this. So here is the final code that compiles and implements the type signature that was required. So in this way, if you find the proof using the derivation rules for example, in the LJT calculus, you can extract the code from it. You infer the code given the type signature. This is the algorithm at work. Oops, there's a formatting problem here. I will fix that in the slides. So the Kerry-Howard library implements this algorithm. It has two main use cases. First, you can define a type signature and you derive an implementation. Let me try to highlight this code. It's hard to see. It's a map function for the reader monad, but in any case, it's a function of a fully parametric kind. It has only type parameters as arguments and as a result. And so then you can implement it automatically. The second use case is to build automatically an expression from previously computed values. So for example, imagine you have some code that looks like this. You have some case class, and you want to find the value of type result given this data. You have a string ABC, you have the function f, and you have a Boolean value true. And there's only one way of doing that. To get a type result, you need an integer and a string. To get an integer, you need to apply f to a string and a Boolean. So you need a Boolean and a string, and then you can apply f, and then you can use this case class constructor and get what you want. The Kerry-Howard library automatically finds this using the Kerry-Howard correspondence and the LJT algorithm in the way I just showed on other examples. The Kerry-Howard library treats these types just the same as type parameters. As I said, the Kerry-Howard correspondence only works for code that is fully parametric. So we must treat these as type parameters. Otherwise, there's no real sense in using the Kerry-Howard correspondence, because I could say, oh, I can always compute a value of type result. I can put an integer 500 and the string empty string. I don't care what it is, the type is correct. So the Kerry-Howard correspondence is powerless in that kind of situation. You can always compute values of type integer or string. The type does not give you any information about how to do that. But if you treat these specific types as type parameters, then the result becomes much more constrained. And in some cases, you can unambiguously find only one code for the type that you want. So this is the practical application of the Kerry-Howard correspondence. Let me summarize. The Kerry-Howard correspondence maps the type system of a programming language into a logic or a system of logical propositions and derivation rules. The proofs of these logical propositions exist only when you can implement the type, and there is a one-to-one correspondence between implementations of the type, in other words, code that has the type that you want, and proofs of those propositions. There's a one-to-one correspondence. Each implementation gives you a proof if each proof gives you an implementation. If the logic of types is decidable, in other words, if there's an algorithm to tell you whether there is a proof or not, then you can take the type signature, follow an algorithm, and automatically produce code, or automatically decide that there is no code possible for this type signature. So a simple, fully parametric code that we have seen, with no recursion, with only type parameters, either the tuple and the unit type and the function type, that corresponds to the logic called Intuitionistic propositional logic, or constructive propositional logic, and that logic is decidable. So algorithms for this logic exist to search for the proof automatically or to search for disproof, the proof that your formula is false. This book I can recommend as an introduction to this logic, how to find the proof and how to find a disproof. This book is very pedagogical. It's a good introduction for this kind of thing if you want to learn how to apply this algorithm by hand. It's not easy, but it is not so difficult that you couldn't possibly do it. So I recommend this book. I would like to conclude by saying that the type-directed reasoning that works with fully parametric functions is a very powerful kind of reasoning about code. This reasoning helps write code. It guides writing code. You look at the type and it helps you to guess and to guess correctly, not just randomly, to have an informed guess about what code could work. And then you have a mathematical theory that shows you that this is actually correct. So you can have an intuition for it, and this intuition is complemented or backed by an algorithm. For example, the Greyhour library and other libraries that implement this algorithm. Because the precision procedures are not very easy to use, especially when there is a disjunctive type, then type-directed reasoning becomes harder. But software engineers can develop intuition so that they almost never need to actually run these tools. And if they run these tools, it will not be blind. It won't be a black box. Software engineers will understand how this tool works, when to use it, and how to trust or not trust the results. So the Curry-Howard correspondence is actually a mathematical theory that helps programmers write code. It's a very unusual situation in programming that mathematical theory actually helps and guides in writing code. And this situation is specific to functional programming. It is not available for other paradigms of programming, such as object-oriented programming, or logic programming, or constraint programming. You could be surprised that logic programming, which is based on rigorous logical theory, does not have the same property, and it is true. Logic programming is based on logic, but programmer is not being helped in writing code by any kind of mathematical theory. The programmer is guessing how to write code, just like the programmer is guessing when writing object-oriented code. But at least for fully parametric functions, there is no more guessing. A lot of functional programming uses type parameters, and this theory shows you that if you use a lot of type parameters such that all of your types are type parameters, like for example in this function, if all of your types are type parameters, then you have a very powerful sort of reasoning based on a mathematical theory that helps you to write code. And so in this way, functional programming becomes similar to an engineering discipline. In engineering disciplines, engineers such as, for example, mechanical engineers, chemical engineers, or electrical engineers, they use mathematical theories to guide them in their designs. They don't just design by trial and error or by tradition. They have mathematical computations and algorithms and formulas that guide them in the design of their products. Functional programmers are in a similar situation. In at least certain cases, such as fully parametric code, mathematical theory directly guides programmers in writing their code. This concludes the tutorial.